Hey guys, and welcome to video 2 in the Big Idea 2 note set for lecture about gas laws. Okay, so we're starting this video on page 3 with gay-Lussac's law. Gay-Lussac's law relates the pressure of a gas to the temperature of a gas. Okay, so this is when it's under constant volume, so it's in a closed container. If you heat it up, what's going to happen to the pressure? And this one should make pretty good sense. If the temperature increases, the molecules are moving more. And if the molecules are moving more, they're gonna run into the walls of their container more. If they're running into the walls of their container more, the pressure goes up. Okay? So as the temperature increases, the pressure increases. So does that mean it's directly proportional or inversely proportional? That means it's directly proportional. So what the equation for this one looks like is like this. It's directly proportional, so that's when we use the fractions. It is P1 over T1 equals P2 over T2. That's how you'll often see it written. Okay? So let's go ahead. There's one more gas law that we need to know about, which is Avogadro's, okay? This should say Avogadro's law. And Avogadro's law is definitely the most complicated. Okay? It says that if you add more gas, it's going to take up more room. I know. Genius. Genius. More gas takes up more room. So as the amount of gas goes up, the volume goes up. Duh. Okay? And this is at a given temperature and pressure. Okay, you can see it here. You have 4 different balloons. If they all contain the same amount of moles of gas, so 0.041 moles in this case, they're all going to have the same volume. And as you increase the number of moles of gas in a container, the volume is going to increase. Okay? Crazy, I know. Let's do an example though. Okay, suppose we have a 12.2 liter sample containing 0.50 moles of oxygen gas, O2, this is bugging me, at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. If all of this O2 were converted to ozone at the same temperature and pressure, what would be the volume of the ozone? Okay. So first we need to figure out what happens when oxygen gets converted to ozone. So if you have oxygen gas and it's converted to ozone, that is not a balanced chemical reaction, so we have to balance it out. Okay? So you need 3 oxygen gas particles to produce 2 moles of ozone, okay? Which is O3. So what this problem is telling us is that we have 0.50 moles of oxygen gas at a pressure of 1 atmosphere and 25 degrees Celsius, but then it's at the same temperature and same pressure, so we don't need to worry about that. Okay, and this takes up a amount of space of 12.2 liters. Okay. Now, we need to figure out if all of it's converted, what's going to be the new volume. Okay? There are a couple ways that we can do this. Okay? The easiest way is going to be looking at the ratios. Okay? So, let's look at this ratio. It is a 3:2 ratio. So, if I have 0.50 moles of O2, for every 3 moles of O2, I'm going to get 2 moles of O3. So the amount of O3 that I'm going to have is 1/3, okay, or 0.33 moles of O3. Okay, that's what's going to happen when it is all converted. We're going to have less moles. If we have less moles, it's obviously going to take up less volume, okay? And they're directly proportional. So if this goes down, if this number is 2/3 of that, the volume is going to be 2/3 of this. Okay, so you could do 12.2 liters times 2/3, and you get 8.13. 8.13 liters. 8.13 liters. Okay, so that's a simple way to do it using the ratio. You could also look at, they have a direct relationship. So you could write it as, let's see, it'll be V over N equals V over N, V1N1 over V2N2. Okay, so V1 is 12.2 over N1.5 equals V2, which we don't know, over 0.33. Okay, easiest way to solve this out, multiply both sides by 0.33. And when we do that, 0.33 times 12.2 divided by 0.5, what do you know? We get 8.1. Okay, I only had 2 sig figs in each of my answers, so I should actually be rounding it all to 8 sig figs. Okay, 8.1 liters. Okay, notice you get the same answer no matter what you did it. It's just a simple ratio type problem. Okay, cool? Okay, cool. Now, what is super convenient is you don't need to memorize all of these gas laws. You don't need to know Boyle's is the pressure and volume, and Charles is volume and temperature, and no, pressure and temperature. See, I don't even have them memorized, okay? Totally unnecessary. The one that I do recommend you memorize, though, that's going to make the AP Chemistry test a lot easier, is the combined gas law. Okay, that's P1V1 over T1 equals P2V2 over T2. Okay, you can also, if you have to, you can also imagine an N there, N2 and N1. Typically, you won't need these ones, but you can imagine them there if you ever run into a situation when you need that. And what's convenient about this is that you can just cancel out whatever is being held constant. Okay, for example, in example number 1, it says at constant pressure, so we just ignore the pressure. Pretend it doesn't exist, and that's fine. Okay, because it's going to be the same on both sides, it doesn't matter if you include it in the equation or not. So let's go ahead and do that first example problem. A sample of methane gas that has a volume of 3.8 liters at 5 degrees Celsius is heated to 86 degrees Celsius at constant pressure. Find its new volume. So we're looking for V2. Okay? So the equation that we're going to be using is V1 over T1 equals V2 over T2. Okay? And whenever we're doing combined gas laws, do not forget to convert to Kelvin. Okay? You have to use Kelvin. Otherwise, you will not get the right answer. Okay? So this is 278 Kelvin, and this is 86 plus 273. 359 Kelvin. Okay, so go ahead and plug it in, see what you get. I'm going to go ahead and solve it out. So, V1, 3.8 liters over T1, 278K, equals V2, which we don't know, over 359K. Okay, the temperature is increasing, so we expect the volume to also be increasing. We'll have to check that at the end and make sure we get it right. Cancels out here. Kelvin units cancel out with Kelvin units. I'm left with liters, which is cool because that's what I want. So I have 359 times 3.8 divided by 278, and I get 4.9. So 4.9 liters is my V2. And what do you know? The volume increased. That's what we expect. We know we did it right. Okay, cool. Okay, cool. Let's go ahead and try the next one. A sample of di-boron gas B2H6. Sorry, typo in the notes. I like it better when it's like this. Okay. A substance that bursts into flame when exposed to air has a pressure of 345 torr at a temperature of negative 15 degrees Celsius and a volume of 3.48 liters. If conditions are changed so that the temperature is 36 degrees Celsius and the pressure is 468 torr, what will be the volume? Okay, so this one, it doesn't look like we can cancel anything out. We're going to have P1, V1, and T1, and P2, V2, and T2. Okay. Don't forget to convert to Kelvin. Go ahead and solve it out and see what you get. Okay, so let's go over it. You don't need to convert the pressure units. It's fine to use anything. So we have 345. Whoa, what happened there? $345 torr. Okay, at a volume 3.48 liters. Temperature negative 15 degrees Celsius, which is negative 15 plus 273, 258 K. And T2 is 36 degrees Celsius, which is 309 K. V2 is what we're trying to find, and P2 is 468 torr. So the temperature is going up and the pressure is going up. So typically more pressure means a smaller volume, but more temperature means a bigger volume. So I can't really guesstimate what the new volume is going to be. We just have to plug it in and solve it. Okay. So again, P1, V1 over T1 equals P2, V2 over T2. I'm not going to put the units in just because it gets a little messy. Just make sure you add them back in at the end. Okay, so 345 times 3.48 over 258 equals 468 times volume over 309. Okay, so let's go ahead and math this out. 345 times 3.48. This side equals 4.65. And then 468 divided by 309 is 1.51 times V. So to get V by itself, divide, and you get 3.08. It's volume, so it's going to be in liters. Okay, cool. Okay, cool. Let's go ahead and do one last problem. A sample containing 0.35 moles of argon gas at a temperature of 13 degrees Celsius and a pressure of 568 torr is heated to 56 degrees Celsius and a pressure of 879 torr. Go ahead and calculate the change in volume that occurs. Okay, so this one I want you guys to do all on your own. The number of moles is not going to change, so guess what? You don't need to worry about it. Okay, you don't need to worry about the things that aren't changing. Okay, so go ahead and solve it out. I'm going to solve it out on my calculator so that you guys can check your answer. Oh, we have to find the volume of that argon gas. Okay, so we're going to need the ideal gas law for that, which is something that we're going to talk about in the next video. So I will go ahead and solve it out and give you that volume first. Okay, so before N is 0.35 moles, Okay, this is giving you a little preview into the next video. Okay, T is 13 degrees Celsius, which is 286 Kelvin, and the pressure is 568 torr. Okay, this is all before anything happens. Okay, we have to solve for the volume, so that uses the ideal gas law, which again we're talking about in the next unit, where P is the pressure. So sorry, my pen doesn't work over there, so I have to do it over here. 568 times the volume, that erg. Okay, 568 times the volume, that's what I'm trying to find, equals number of moles. Okay, R is a constant, okay, it's called the gas constant. And when we're working in torr, you can always check your equation sheet for the gas constant. See, like it says gas constant R right there. Ooh. Okay, and in torr it is 62.36. And then the T is 286. Okay, so when I solve this out for V, I get 10.99 liters, which, because this only had 2 sig figs, I'm going to go ahead and round to 11 liters. Okay, so now we can ignore the end. We have our T, our P, and our V1. And then our T2 is 56 plus 273, 329 Kelvin. Okay, and our P2 is 897 torr, and we're looking for our V2. Okay, so go ahead and plug that into the combined gas law and solve it. Okay, so 568 times 11 over 286 equals 897 times V2, which we're looking for, over 329. Okay, and you should have gotten 8.01 liters as your second volume. Okay, cool? Okay, cool. Check out the next video for the ideal gas law, which is this one right here.